All right, hi everybody. My name is Michael Ram. I'm an assistant professor at the University of Massachusetts, Boston. I'm also the lead of the Ubiquitous Communications and Networking Lab, or UCAN Lab, at UMB. And my talk today is on this concept of software-defined radio beyond the radio spectrum. In particular, it's going to be talking about our work as a out-of-tree module for GNU Radio, focused on optical wireless communications. And for those of you who may be not familiar with what we're doing here, we're talking about indoor optical wireless communication systems, things like visible light communications or Li-Fi. Kind of an extensive author list. The backstory here is this was actually a collaborative project. Two senior design teams worked on this over the past year. My team at UMass Boston up towards the top, and then also with my colleague Hovannes Kalhanjian at CSU Fresno. We heard one of his students, his grad student Gregory, talk earlier, plus a group of senior design students working with him as well. I also want to call out Arslan Ahmed, who is a student at Leeds Beckett University who collaborated, worked with me on this, and he spent a lot of his time developing the GRWC out-of-tree library. So that outlines what we got here. Quick motivation, background, some reasons why we're looking at SDR applications for optical wireless communications. I'll talk a little bit about our systems overview and introduce this concept, software-defined optical wireless communications. We'll talk briefly about the software design, what we're doing with this out-of-tree module, GROWC, and then I got some videos and demos talking about our hardware integration, a little bit of optical wireless systems, how we brought this to experimental practice, and some of the stuff we're starting to look at into from a systems perspective related to multiplexing and multiple access using DC biased optical OFDM or OFDMA, and also wavelength division multiplexing and WDMA multiple access. So starting with our motivation, and I sort of borrowed this Venn diagram idea from someone's presentation from a few years ago. I don't remember what it was, but related to RF NOC and overlap of FPGA experience and wireless comms researchers. So similar idea here. We got this great pool of wireless comms researchers doing excellent stuff in radio. Big pool of people working in optics research from the physics space. And then in the middle, we sit here working in the space of optical wireless communications. Like I said, the visible light comms ideas, but also infrared communications, fiber optics communications, things like this, for free space optical communications. So the key concept that we're coming into with this project idea is we're looking to see how we can get more people with this comms experience interested, excited about, and working with experimental optical wireless communication systems. Similarly, on the other side, people working in the optics space, we're looking to provide some tools and support that bring people working more at the physical properties side of things into systems implementations that actually deploy optical wireless communication systems. So big picture, we're looking to make more tools that make this experimental research in optical wireless communications more equitable, more accessible, more available to both communities. So a little more background about tying to these two things. Optical wireless communications, been around for a while. Infrared specs in the early 802.11 Wi-Fi protocols, seldom used, but there. And there's been a lot of interest over the past couple decades of sort of advancing this technology, particularly with the development or advancement of LED technology for illumination grade lighting LEDs, light quality luminaires. So we see a lot of work in physical layer, point-to-point communications, developing systems that can transmit data. But more recently, in the past few years, there's a lot of interest in higher layer integration and developing optical wireless communication systems. Right? So how do we get multiple users, multiple cells in a space where a resource allocation, dynamic environments with handover, much of these kind of problems. And the reality there is that there's a lack of openly available tools particularly with real-time signal processing capabilities that provide some sort of performance analysis at these higher layers. Lots of great simulation tools, lots of real high quality optical equipment for point-to-point links, but when you get to this systems analysis, it's a little bit lacking. On the other side, something we're all familiar with here, the software radio background, excellent opportunities to develop dynamic systems, adaptive RF systems, and also to kind of bring in this high-speed RF prototyping of novel ideas, put some signal processing waveform onto a physical piece of hardware. And in general, this open access SDR tools over the past 2 decades or so have really created this opportunity for a lot more people to get in this space of working with experimental RF systems, right? What we're doing is extending this software-defined concept out to the field of optical wireless communications and sort of trying to adapt these two things. Now, I just want to point out that this is definitely not a completely novel idea. Some of you might have heard of some of this before. I've been working in this space in some way or form for over a decade to use GNU Radio for a variety of different optical wireless applications. This is a simple video stream demo from back in 2011. A bunch of other references, people using software radio for optical wireless communications. But the key here is that a lot of this prior work is mostly developed for specific research focus. So you're trying to get a single instance of something, see how it works. Maybe it's a modulation scheme, single tool, single signal processing chain. And the source code and the hardware design is not openly accessible. So we're trying to address that and make an openly available software repository that ties both the signal processing aspects of optical wireless communication, some of these tools that we've developed there, with some easily defined software-defined radio front-end hardware that adapts with existing equipment like the USRPs. And so we'll talk a little bit about the system objectives or kind of the system overview. For those of you maybe not familiar as much with optical wireless communication, some of the unique characteristics here, particularly visible light communications, Li-Fi type problems. We're looking at intensity modulation with direct detection. So you're driving a current signal into an LED directly proportional to your optical power output. That optical power is picked up at a photosensor, converted back to a current and received at the other end. It's highly directional and there's minimal multipath impacts. So the biggest things that impact a system or an implementation of this are things like your emission pattern, what your LED emission pattern looks like, and what your receiver profile. So common characteristics or similar characteristics to maybe millimeter wave or other highly directional comm systems. And we also have this nice capability up here that we're looking at potentially changing different color channels, similar to what you can think of different wavelength channels in fiber optic systems, but doing with red, green, blue color channels, for example, to create a white light luminaire. As we think about bringing this to a systems level, as I mentioned, this is where there's a lot of really interesting problems. So if you think of a room like this, we can, I mean, this isn't the best example, but these little overhead LED lights, you can kind of picture that if they're spread out through a space, you have your own individual private hotspot, your own resources in a space or a conference hall like this, you get a much broader aggregate capacity potential, right? So you're getting spatial reuse at a very unique scale, similar to millimeter wave or potentially terahertz type communications. But in a system like this, if you have these transmitters, there's a lot of overlap areas. You got to think about resource allocation of neighboring cells, like you have potentially here for this device. I don't know if you can see my mouse over there, probably not, maybe. Or similarly for these two devices, sharing resources across users that fall within a cell. And then if you talk about dynamic environments, we have to worry about handover things there. More broadly, heterogeneous networks, so thinking about coexistence with RF communications. Can we develop systems like this? We've done some of this work in the past using our SDR optical systems with RF communications as well. And then multiple use of the optical system. If you're generating waveforms, sending signals, you can do other things like visible light positioning, where you're sending a unique waveform as beacons from a bunch of different cells using triangulation, trilateration type topics to do indoor localization. So that gets us to a kind of system diagram. I'll start with a point-to-point link, how something like this gets implemented, kind of the backstory. We all are familiar with this flow. We have our PC with our SDR software, lots of different tools there, front-end hardware, lots available, and then kind of breaking up the front-end SDR hardware from the communications components, right? RF space, we're typically talking about different antennas. If we step through this from the optical space, first off, narrow it down to GNU Radio. That's why we're here. We're working with this out-of-tree library, GROWC, that we're developing for some of our modulation and channel models for optical wireless communications. In terms of the SDR hardware, we're focusing specifically on the USRPs with modular daughter cards. With the intensity modulation direct detection, we're basically operating close to baseband. So we need, or in this case, we're implementing with LFTX and LFRX daughter cards in there. And then in our front end, we have this modular capability to swap out what we're controlling to either generate the light or to pick up some optical signal at the other side. So lots of different photosensor capabilities, Thor Labs as options, different LED boards, simple white light LEDs, different color channel LEDs that we'll talk about in a bit. And this modular design allows us to do a lot of really cool testing at the systems level because we can generate our waveforms within SDR or within GNU Radio and then apply them to different front-end hardware to see how this performs if your emission pattern is broader, more narrow, different optics channels, filters, lenses, all this kind of stuff we can play with. The workflow for this is probably something we've all seen before, starting with something that we can simulate. So we developed these GRWC channel models that are more specific to optical wireless communications, and the DC channel gain dependent on location, position, orientation, noise characteristics that are more specific to optical wireless. We can extend this to a loopback system on a single USRP, a single PC, and then eventually get this to a point-to-point communications where we have a transmit side and a receive side, maybe make this duplex after that. With that in mind, we'll go through a little bit of the software side, and this is work that's been presented before. We have a WIMA wireless mobile communications paper tied to this GROWC library, so I won't spend too much time on this, but the basic idea is it's developed as an elder tree library or elder tree module for GNU Radio. And our hope is to implement this in a way where we sort of have the user plane and developer plane for this. User plane, we have some existing blocks for the channel models that I've mentioned, a bunch of different unique pulse modulators that do things like dim the lights and also incorporate data transmission, and then applications for optical OFDM techniques. Some of the simple sample flow graphs that we have in there as examples include this DC biased optical OFDM, which I'll talk about in a minute. And we're in the process of adding in these additional flow graphs for OFDMA and wavelength division multiple axis for a multicolor channel. So we can use that in simulation, and the big benefit of all of this is being able to export it to experimental type systems as well, where we can then align our parameters of the software to that front-end hardware. And as we're building this up, it's still in the relatively early stages, but the hope is to bring in more people in the community to start working or to help work with this or to potentially build off this, the optical wireless space, or if there's anybody interested in these kind of problems, to help develop and improve on this library. So I'll start with a very brief overview of the optical wireless channel model that we have in there. If we think of this system in the top right here, we're looking at a simple example where the key benefits or the key challenge, whichever way you want to define it, for optical wireless communications is this directionality and the impact of emission direction and acceptance direction. So we'll take an example where we're simulating the channel going from left to right on this image, basically two separately well-aligned communication links where there's minimal interference. If we bring that RX2 over closer to TX1, we're getting interference on both sides, picking up both of those signals. And then the impact of orientation, as we rotate that RX2, we get to see a stronger signal from the original transmitter, even though we're closer to that first transmitter. And this is just built up, this is that elder tree module, or one of the elder tree blocks in this module. We have different channel modules for relative location, so specifically parameterizing the distance and the rotations of the transmitter and receiver. And then for absolute position and location, where you're just defining what the locations are of the transmitters, XYZ location for transmitter receiver, and the three-dimensional rotational vector there as well. All right, so it's scalable for multiple transmitters to get this characteristic of interference to see how overlapping cells could potentially interfere on multiple receivers. We can adapt the parameters over time. So this is an example of running through this case, just a single sinusoid, low frequency, but you can update too. So two different sinusoids, one from each transmitter. If we kind of see what's happening here for our receiver, this is this RX2 as it moves from directly below transmitter 2, where this 1 kilohertz signal is very strong. If we move in the second middle block here, we've moved over, and now the TX1 10 kilohertz signal is stronger, but then if we rotate it, we can see that we're actually still getting a decent signal from TX2, even though the actual location is closer to transmitter 1. And this is just another way to kind of view it in time domain, but with the three different receivers picking up at the same point. Right, so just one out of tree module. The key characteristic is now bringing this into practice. Right, so building out a tree model, kind of putting in this theory into there and simulating it is great, but we like to see how we can actually bring this to experimental practice for evaluating real-world systems, potentially testing with different hardware as well. In a broader multi-cell, multi-user design, one of the things that we benefit from using the LFTX and the LFRX is that as a baseband system, we're really sending two separate IQ samples, two separate signals on your I and your Q channels. So we can drive 4 different transmitters with a 2-channel X310. Basic idea is that we have no passband modulation, so you can draw out the I and Q channel as two separate real valued signals and derive two separate transmitters. Two separate optical transmitters. Right? Then we have our optical channel, multiple USRPs, and so on. On the front end hardware side, we get some other potentially discrete components, potentially something that we built together. We got our amplification and bias in order to operate in the linear range of an LED or whatever this optical driver that we have. Potentially some transmitter lensing to vary what that emission pattern looks like. And then on the receive side, a bunch of individual components as well. You have optical filters to select a range of optical frequencies, some different color channels, your lens, photo receive, the actual receiver, and then afterwards some amplification, anti-aliasing, and blocking. We have a DC signal, so the DC blocker helps us bring it down to an AC. Altogether, we can package these in various components or use it as discrete parts. These are a couple of different devices, some commercial, some that we've built. So these receivers on the right here are photosensors of different varieties from Thor Labs. You got some with transimpedance amplifiers over here. This is an avalanche photodiode. You can notice the difference in the pixel size of these three different receivers. So that has a characteristic that impacts our performance and potentially how we would build that into a system in the future. This is a commercial product from a company called Hyperion Technologies. They sell this. It's a higher bandwidth, up to 20 megahertz. Optical communications link. And then what we have over here is a $2 or $3 LED array that we can implement very cheaply, has a bandwidth of maybe 3 megahertz to do some testing. And our custom board here, which is a multicolor board using RGB LEDs with 3 separate channels that we can drive individually from one of the X series USRPs. And then in addition to this modularity of swapping out the hardware, we can also play around with the lensing, like I mentioned. For example, on your receivers, we can put different color filters on top of here and different lenses to either narrow or expand what that field of view looks like. All right, so the fun part, let's take a look at some videos and actually see what's going on here. This is just to get our initial view of the system. We got our, maybe I'll go this a little bit slower. Oops, if I can back up there. So on this side, on the transmit side here, we have the USRP passing through some two DC bias Ts, RF bias Ts to bias your signal into the linear range of the LEDs. Both of these little low-cost LED arrays right now just sending a sinusoidal signal and picked up at the two photosensors at the other end. And as we zoom in here, you just kind of see, noticing if we block either one of the channels, one channel goes away, and then the other channel goes away. And what we can notice here is still that even though this is that kind of nice aligned two-channel system, even with some high directional optics, we're still picking up both of those characteristics, or both of those frequency components. So you're still seeing signal from both of the transmitters, which gets us into the open questions that we're looking into for multiple access, resource allocation, and so on. And you might also notice this other little component over here, which is actually relatively low sampling right here. We're looking at something that actually picks up the pulse width modulation of your overhead lights in the ceiling. We can kind of see this in another video. If we're starting in that nice dark room, we turn on the light, right, and that little peak came up, in this case, somewhere over here, just to start recognizing that. So that's important. We'll come back in a little bit just to kind of talk about some of the stuff we did with our DC OFDM and subcarrier allocation. But that gets me to this point of thinking about some of the key factors for implementing a system like this. So we have particular characteristics that may be a little bit different for this front-end hardware with optical wireless communications. In particular, finding that linear range, similar to power amplifiers for RF systems, but this is the direct output signal that comes from this. So if we take this visual of the relationship between the transmitted voltage drive signal and the received signal at the other end of the optical receiver, we got this thing that starts initially maybe looks like an ideal diode, but we know nothing's ideal, so there's actually some nonlinearities down in this region right here. Just recognizing this, we send our sinusoid through, we can see these harmonics if we either shift the DC too low, so if we haven't biased it up enough, or if we make the amplitude of our signal too wide, in which case it ends up in those nonlinear regions. So point to bring up all of this is just there's some interesting applications. We're directly driving this out afterwards, so you can do all of this pre-distortion in the digital domain. There's definitely some interesting potential applications of DPD type problems. So if anybody's done some of that with RF amplifiers or looked in anywhere with that in the past, I'd be interested to discuss something like that for future work. And you can skip through this one quickly. Basically, this is just the same idea. We're increasing the amplitude at the transmitter, and you're seeing those harmonics that start popping up. Now to actually start looking at some data transmission, the thing that shows up in this GROWC, the module that we had, in order to adapt OFDM techniques for the optical spectrum, we need a real valued signal, right? So there's no passband, there's no carrier modulation, so we need to start with a real valued signal. So one of the simple ways to do this, if you're familiar with older discrete multi-tone, kind of early implementations of OFDM type subcarrier or multi-subcarrier problem, what you do is you take your positive subcarriers, you take the complex conjugate, put it as the negative subcarriers, and when you do your FFT, you end up with a real valued signal. So this application lets us do all that implementation in the waveform generation process, and we end up with this. I don't know if the audio is going to get picked up, but we'll see so as we start sending. So there's your digital modulated audio file. We can do this with text files, eventually get up to video, some of the stuff like I mentioned what we showed before. As you notice from what's happening here now is we're actually doing a small rotation of the receiver, and the channel characteristics get pretty poor. Right? So that's because we have this lens, this optical lens on there that's focusing the optical power directly on that active photosensor area, which is great for a high quality signal, but not great for mobility if we're talking about moving this thing around. So lensing allows us to do that. Just another sort of same demo, we've moved the receiver closer to the transmitter, take away the optical lens. We kept our filter on there, but now we get 45 degrees of rotation. We can get a lot more flexibility in that. And you notice the signal power in our waterfall is staying relatively the same. Basically, you're getting the cosine law characteristics of that receive power, but majority of it is just the signal there. So without lensing, the rotation has less of an impact. All these are characteristics that we're exploring when bringing this up to a system design. What's the best way to implement something that can be moved around an environment and still pick up signal, or also potentially allocate to different transmitters? This video now takes that DC OFDM waveform and ties it back to some of those characteristics like the light interference we looked at before. Basically, we're doing a manually selectable subcarrier assignment in the system. So regular OFDM signal chain with that Hermitian symmetry in the middle, starting off with the low frequency subcarriers, or the lower subcarriers. And see as that get blocked, we lose the data. But if we change our receiver over to looking at the higher frequencies, stops receiving anything until we go back to our transmit side and adjust to start sending on the higher frequency subcarriers. And we start picking up data again. But with a system like this, so this is great for multiple access, right? We can use low subcarriers for device 1, higher subcarriers for device 2, but also for interference mitigation. If that signal is in the middle, we can look for a spread selection of frequencies, which may or may not show up that well over there, I'm not sure. But you can see over here, our spectrum's actually using something like subcarriers 8, 9, 10, 11, and 20, 21, 22, skipping that spot where there was that interfering signal. All right, so this gives us the flexibility benefit to do this. We're looking at doing a more dynamic system that adapts in real time as well. I'm not sure what my timing is left on here, but all right, good. So kind of wrapping up with one last example. I mentioned the color channel part of things as well. I don't have the best videos for this. We didn't get to reset the system. This was something that one of my senior design teams worked on last year. Basically, they built this board. It's a multicolor transmitter. One of the things, it was a group of electrical engineers. They were much more interested on the hardware side than the coding side. So they did a little more on this, and they also built up a little steerable transmitter as well. Let's see if this video plays, hopefully. And I'll go through it kind of slowly here. So in the system, we have basically right now just sending 2 sinusoids to show something. Perhaps it has this bandwidth across here. This is the receiver over on the right side in the space, and this is the receiver over on the left side of the space. They're both just kind of collected back at a single USRP, but they're distributed in space at the moment. And as we go through the video, you see what happens. We can steer the light. This is just mechanical steering to direct from being received by this first one. We're slowly sweeping it, so now we're picking up the signal over here. And then if we snap back to, in a second, Should jump in a second, perhaps if the video is still going. Yeah, right there. So now it just kind of sweeps over to the other side. So steering capabilities, again, mechanical steering, not the ideal, but something that shows some nice proof of concept implementations. And the last video here follows the same similar setup. This one loads. Except now this is giving us the benefit of multiple axes. So one of the last things I mentioned there was we have this option of doing color channel selection. So if we put different optical filters on our receiver, we can pick up different signals from different color light emitters or whatnot. Right? Each one of these LEDs is a RGB LED, so we can control a red, blue, or green signal. We can do this for multiplexing to send 3 separate transmissions simultaneously, or we can send a different color on different channels for intended for different receivers. What we'll show here is sort of using this for interference mitigation. So again, looking at your received signal, we're looking at the blue color channel. Saw that in the ceiling. We have these 2 receivers. One's a blue filtered receiver and one's a red filtered receiver. And what happens here is, oops, if I go back to that, control's not the greatest. One more second. Okay, in the ceiling, we have this other device that's just a single LED transmitting a blue light, and it's just basically something to intend or to apply interference. So it's interfering in the blue color channel. Maybe it's a jammer, maybe it's another transmitter that's using the blue light signal. And on our receiver, we see this peak in the middle. So if we say this was the bandwidth of our actual intended waveform, this thing shows up right in the middle. It's not ideal. What we can do is then go back over to our transmitter and switch from our blue channel to our red channel. And we'll notice that the received signal sort of loses our intended signal, but keeps that blue interference as this goes away. And then if we come back over to our receiver, we're basically going to switch so that we're now looking at the red color channel. And we've mitigated that interference because it's still on the blue side. We're now transmitting on the red channel. All right, interesting stuff, kind of very low-level demonstrations right now, but now we're trying to merge all this together to apply some of the actual OFDM waveforms, the communications, and see how we can do some of this stuff in real time as actual multi-user, multi-access type problems for optical communications. So plenty of ongoing additional work. Like I mentioned, the actual resource allocation, particularly doing this more dynamically, taking those DCO-OFDM subcarriers, assigning them based on this current system or color channel as well. We've done some stuff with a duplex design, so implementing back channel with RF communications, and then rather than the audio, we've done some video transmissions with GStreamer as well. Future work, ideally we'd like to get this moving a little bit faster. We can increase the bandwidth up to 5 megahertz for our designs or up to 20 megahertz for that Hyperion Tech device, but trying to think about porting some of this off into RF NOC. Other waveforms that we're working at, there's a bunch of different optical OFDM type of waveforms that try to do things like color dimming or channel dimming to change the color of your light or to change the brightness of the light. Packetization, much more things that can come as part of this tool. Big picture outcome, and just to summarize, the idea is that we're trying to integrate within GNU Radio to create this open source tool for optical wireless communications researchers. There's some foundational building blocks that we're starting with, including some basic modulators, demodulators, the DCO-OFDM blocks, some sample flow graphs, and so on. And then integration into higher layer tools, but also just integration with hardware and giving a better description of how to bring something like this from a simulated system into something that's experimental. If somebody's interested as a student project, you can kind of introduce this idea, get them up and running relatively quickly. Right, so applications of this, the tools, the SDR techniques and tools to optical wireless communication, there's value for us as experienced researchers in optical wireless, looking to do these higher systems level problems. Also for people that are looking to potentially look into optical wireless communications as sort of a getting started stage. If you have some USRPs and you want to buy a couple $10 LED boards, maybe a couple $100 photosensor receivers, you could probably build up a system that looks like this. So thanks for listening. Thanks all for your time, and thanks for all the GNU Radio folks for organizing and for everything else. Appreciate it.